Let's look at an example of a 3D approach to a problem in Python, although this will work for any language. Let's ask a question. Is the following a good bet? Suppose that for $10 you can roll a single die repeatedly for as long as you want. An hour, 2 hours, 10 hours. If you ever roll more than 7 of the same number in the sequence, you win $1,000. If you ever roll more than 11, you get $1 million. For example, here's a $1,000 winning roll, where eventually you got 8 fives. Here's a $1 million roll, where eventually there were 12 threes. Now, we have to begin with definition. Computers are tools, so that means we have to ask the question in a way that the tool will understand the problem. Is this a good bet? It's not something a computer is going to understand. Instead, we need to come up with a question in the context that a computer can understand. We need to figure out how many tasks we're going to need to answer that, and we're going to need to use good names. We're going to call this the longest constant subsequence problem. The question we're going to look at is, if you roll a single die a large number of n times, what can we expect to be the longest constant subsequence of consecutive rolls of the same number? Notice we have 2 tasks. We're going to have to simulate a large number of rolls, and then the main question will be determining what the longest constant subsequence is. These 2 tasks are very different. I would not try to write a program that did both of these in the same procedure. Simulating dice rolls, you're going to be given the number of dice rolls you want, and it's going to be simply a list of uniformly random rolls. The longest constant subsequence task is, given that long list of rolls, you're going to determine what the length of the longest constant subsequence is. We want to design with inputs, outputs, and flow. Inputs for simulate dice rolls is going to be the length of the list that we want as the output. Longest constant subsequence, the input is going to be a list of dice rolls. We want to think algorithmically. So what is our goal? What is our starting point? And most importantly, what is the next step toward reaching that goal? So for simulate dice rolls, we just need to create an empty list and then append random integers between 1 and 7 to that list. The only design requirement we have for this task is we're going to need to know the Python syntax for generating random numbers, which we'll see later. The other task, the longest constant subsequence, has a little more design element to it. We want to start with examples so we get a feel for exactly what we're doing. We don't want to use trivial examples. We don't want to have, for instance, an entire constant sequence to begin with. And we don't want to use special numbers if at all possible. Now, we do want to use trivial examples in special cases as tests, but not as initial design tools. Now we want to think in a loop table mind frame, a what happens next mindset. So for this example, here's what we're thinking. 1 is a constant subsequence of length 1. 1, 2 is not constant. So now we're going to start over and say that the longest constant subsequence to this point has a length of 1, and we're currently in a constant subsequence of length 1, starting with this 2. 2, 2 is a constant subsequence of length 2, so now we update our longest as we update our current length. And notice we're just going to think algorithmically, one step at a time as we go across here. 2, 2, 3 is not constant. Now 3, as our current subsequence, it has a length of 1. 3, 2 is not constant, so 2 is our new subsequence, and it has a length of 1. 2, 5 is not a constant subsequence, so now 5 itself is our current subsequence. It has a length of 1. 5, 5 is constant. It has a length of 2. So our current subsequence of 5, 5 has a current length of 2. 5, 5, 5 is a constant subsequence. Notice we're up to here now. 5, 5, 5. It has a length of 3, so the current length goes to 3, and that is also now the new longest. 5, 5, 5, 5 is constant. that means the current subsequence has a length of 4, and that is now our new longest. But 55554 is not constant, so we start over with the 4. Now we have a subsequence of the single element 4 with a length of 1. 4 is constant, length of 2. 4 is not constant, back to 1. And now we know that the longest constant subsequence has a length of 4. Now, let's look at our inputs and our outputs for this procedure. Our input is a rows list. Our output is going to be the length of the longest constant subsequence. We're going to give the name longest. Our flow, which we infer from the example previously, is that we're going to have two variables, current length and longest, and they're going to interact with each other in that as we loop over items in the list, we're going to see if the current item is the same as the previous one. If so, the current length is going to increase by 1, and then we need to check and see, is it now the longest? Now here's a loop table which looks at this exact same idea. So what we're going to do, as you've seen already, is except for the first entry, I've taken the entries in this list and I've put them down here, and I've initialized the current length to 1, the longest to 0. Now I ask the question, is 2, this 2, the same as 1, which is the first entry in the list? That's false. And so since that's false, the current length is 1 and the longest is 1. The next entry is 2. So now I have 2, 2, which corresponds to this 2, 2. Those are the same. That's true. We increase the current length by 1, and now we have 2, indicating that this subsequence has a length 2. The longest is also now 2. Then we get to 3, and so 3 is not the same as 2, and therefore we go back to a current length of 1. And if we continue in this manner, eventually we'll get to the 5555, which you see here, and 5 is the same as 2. No, that's 1. 5 is the same as 5. True. Up by 1. 5 is the same as 5. True. Up by 1. Increase the longest to the current length. 5 equals 5. True. Same. And so on and so forth. We notice that we have to start with the j equals 1 entry in the list. So indexing starts at 0, so j equals 1 is the second element in the list. And we also notice we're going to return the final value of longest, which in this case is 4. Here's a flow chart that shows this exact same idea. Helps us track our logic. We start with a rows list. If we initialize to j equals 1 and the rows list is going to be a length of n, we go through here updating current length according to the answer to this question, just like we did in the loop table. Here's a more official version of a flow chart. So we tend to use diamonds for branches when we make decisions. And so we keep checking and repeating this process until these are the same, in which case we return the longest. Now, at one point in time we used pseudocode, but if you'll notice, pseudocode looks an awful lot like the actual Python. And that was intentional. And so now, once we've done a flowchart, a loop table, we have some design element completed, we can go straight to the Python. So here's our final implementation. For simulate dice rolls, before we write this program, we need to know how to generate random numbers from 1 to 6, including both the 1 and 6. So we look at random, the namespace, and it has a method or procedure, randent, attached to it. Randent takes us from a low to a high, low inclusive, high exclusive, and therefore we can put 1, 7, and that will get 1 up to 6, but not including the 7. So here's our implementation. Here's our roles. We keep appending random numbers to it, and once we get through, we return the roles. That's our list. And our longest constant subsequence is initialized. We enter the loop. Notice we start at j equals 1. We check to see if the current is the same as the previous. If it is, we increase the current length. Otherwise, we reset it. We see if we need to update the longest, and once we've completed this process, we return the longest. Here's some tests. So here's 100 dice rolls, a list of 100 numbers from 1 to 6. Here's 20, and notice that longest constant subsequence rolls tells us that 4 is the longest constant subsequence, and sure enough, there it is, 6666, and that is the longest. So now we're ready to answer our question. We simulated 100,000 people, each rolling 1,000 times. So we started with trials as an empty list, and for each of the 100,000 people, we generated one number, their longest constant subsequence in their 1,000 rolls. And then we looked at a histogram. We found, for instance, that about 50,000 people had 4 for their longest constant subsequence. A little over 35,000 had 5 for their longest constant subsequence. And you'll notice there were a few winners. In particular, the casino made $1 million, 100,000 people times $10 each is $1 million. 42 people won the $1,000 prize, so the casino made $1 million, paid out 42,000, and nobody ever won the $1 million. So is this a good bet? Well, it depends on your perspective. But for me, I'd probably do something else with my $10.